Welcome! In this session, we'll explore an intriguing coding problem titled Distribute Coins in Binary Tree. This problem challenges us to efficiently redistribute coins across a binary tree structure to meet specific conditions. Let's dive in and break it down step by step. In this problem, we are tasked with redistributing coins in a binary tree to ensure that every node contains exactly one coin. Each node in the tree has a value, node.val, which represents the number of coins currently at that node. The total number of coins is equal to the total number of nodes in the tree, meaning that there are no missing or extra coins overall. However, the distribution of these coins may be uneven across the nodes. To redistribute the coins, we can make a move, which involves transferring one coin along an edge connecting a parent node and its child. The objective is to determine the minimum number of moves required to achieve the desired state where every node holds exactly one coin. The input is given as a binary tree structure, and the output is an integer representing the minimum number of moves needed. To better understand the problem, let's look at the first example. Here, we have a binary tree with 3 nodes. The root node has a value of 3, meaning it contains 3 coins, while its 2 children each have a value of 0, meaning they have no coins. To balance the coins, we need to make 2 moves. First, we transfer one coin from the root to the left child, and then we transfer another coin from the root to the right child. After these 2 moves, each node will contain exactly one coin, which matches the requirement. The output for this example is therefore 2, representing the 2 moves needed. In the second example, the tree has 3 nodes as well, but this time the left child of the root contains 3 coins, while the root and the right child have none. To balance the coins, we need 3 moves. First, we transfer one coin from the left child to the root. Next, we transfer another coin from the left child to the right child. Finally, we transfer one more coin from the left child to the root. After these 3 moves, each node will have exactly one coin, so the output is 3. Meanwhile, in the third example, the tree consists of a single node with one coin. Since it already meets the requirement, no moves are necessary, and the output is 0. Now, let's go over some additional notes and constraints. The number of nodes in the tree can range from 1 to 10,000, and the value at each node will always be between 0 and the total number of nodes. The problem ensures that the total number of coins equals the total number of nodes, so there are no missing or extra coins. Our task is solely to redistribute the coins efficiently. Each move involves transferring one coin along an edge, and multiple moves can be made along the same edge if needed. A key insight for solving this problem is to use post-order traversal of the tree. By calculating the excess or deficit of coins at each node recursively, we can accumulate the total moves required to achieve the balanced state. This approach ensures an efficient solution to the problem. To solve this problem, let's start by analyzing different approaches we could take. The brute force approach is the most straightforward idea. Here, we try all possible ways to redistribute coins across the binary tree to balance the nodes. For each node, we would traverse the entire tree and determine how many coins need to be moved. However, this method is highly inefficient because redistributing coins involves a combinatorial number of possibilities, leading to an exponential time complexity. Given the constraints of the problem, this approach is not practical for large trees. On the other hand, the optimal solution leverages a tree-based depth-first search, or DFS, strategy. The intuition here is that the total number of coins in the tree is fixed. Therefore, the problem becomes minimizing the number of moves needed to ensure every node has exactly one coin. A move is defined as the transfer of a coin from one node to another along an edge. By using a post-order DFS traversal, we can treat this as a flow of excess coins. For each node, we calculate its balance, which is determined as the node's value plus the balances from the left and right subtrees, minus 1. This approach smartly propagates the excess or deficit of coins through the tree, allowing us to compute the minimum moves required efficiently. With this DFS approach, the process becomes clear. We use post-order traversal to calculate the balance at each node. A node's balance represents the number of coins it needs to give away, if positive, or how many it needs to receive, if negative. The total number of moves required is simply the sum of the absolute values of all these balances. This systematic traversal ensures that the redistribution of coins is efficient and avoids redundant calculations. Now, you might wonder if a greedy optimization could work. In a greedy approach, we would consider local adjustments, moving coins between nodes without accounting for the global balance of the tree. However, this method fails to guarantee an optimal solution because it doesn't consider the overall structure of the tree. The problem requires a holistic view, which a structured traversal like DFS provides. Ultimately, the chosen strategy is the DFS method, and it stands out as both optimal and intuitive. Post-order traversal enables us to calculate balances for child nodes before handling their parent, ensuring the flow of excess coins is handled correctly. The number of moves at each node corresponds directly to the magnitude of its balance, and the total moves are derived from the sum of these absolute values. This approach is not only elegant but also computationally efficient. Let's see how the DFS implementation works in practice. The function starts by defining a recursive helper function, DFS. For each node, the helper function first computes the balances for the left and right subtrees using recursive calls. Then, it updates the total moves by adding the absolute values of these balances. Finally, it calculates and returns the balance for the current node using the formula, the node's value plus the left and right balances, minus 1. This ensures that the excess or deficit from this node is accounted for as we move up the tree. The overall function initializes the moves variable to 0 and invokes the DFS function starting from the root of the tree. Once the traversal is complete, the total moves required to balance the tree are returned. In terms of complexity, this approach is highly efficient. The time complexity is O(n), where n is the number of nodes in the tree, because each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. This makes the approach well-suited for both balanced and unbalanced binary trees. The methodology works because it fully leverages the structure of the binary tree. By using post-order traversal, balances are propagated from the leaves to the root in a systematic way. This ensures that no excess or deficit is overlooked, and every move is accounted for. The use of absolute values simplifies the calculation of moves, making the implementation both efficient and easy to understand. While the recursive DFS implementation is straightforward and elegant, it relies on the call stack for handling recursion. If stack space is a concern, an iterative approach could be used instead. However, this would introduce additional complexity to the code, making it harder to implement and debug. For most practical cases, the recursive solution strikes the right balance between simplicity and efficiency. In conclusion, the DFS approach is the ideal strategy for solving this problem. It combines optimality, clarity, and computational efficiency, ensuring that the minimum number of moves is calculated effectively. By leveraging the binary tree structure and using post-order traversal, it minimizes redundant calculations and handles the redistribution of coins systematically. Alternative methods like brute force or greedy optimization fall short in either feasibility or optimality, making DFS the clear winner. This strategy not only provides the correct solution but does so in a way that is both elegant and scalable for larger trees. To solve the problem of redistributing coins in a binary tree, we first need to understand the concept of excess and deficit. Each node in the tree starts with a certain number of coins, and the ideal state is for every node to have exactly one coin. If a node has more than one coin, it has an excess, and if it has fewer than one, it has a deficit. The excess or deficit at any node can be calculated as the number of coins at that node minus 1. The challenge lies in redistributing these coins between connected nodes, using the fewest possible moves. Since each move involves transferring a coin between a parent and child node, our goal is to minimize the total number of these moves. To achieve this efficiently, we can use post-order traversal, which processes child nodes before their parent. This helps us compute the net coin balance for each subtree and resolve imbalances locally before propagating them upward in the tree. Post-order traversal is key to implementing this algorithm because it allows us to handle child nodes first and then process the parent node. To begin, we define a helper function called DFS node that calculates the net coin balance of the subtree rooted at any given node. For each node, we recursively determine the balances of its left and right subtrees using the DFS function. The current node's balance is then computed as the sum of its own coin value, the left balance, and the right balance, minus 1. This calculation reflects whether the node has excess coins to give away or a deficit that needs to be filled. To account for the moves required, we add the absolute values of the left and right balances to a global counter called moves. These absolute values represent the number of coins that must be moved to or from the child subtrees to resolve their imbalances. Finally, the node's balance is returned to its parent, ensuring that the excess or deficit propagates upwards in the tree. One of the key insights of this algorithm is that each subtree's excess or deficit is resolved locally before that balance is passed on to its parent. This bottom-up approach ensures that the total number of moves is minimized. The absolute value of a node's balance at each step directly corresponds to the number of moves required to redistribute coins within its subtree. By sticking to post-order traversal, we process child nodes first, which allows us to efficiently handle imbalances starting from the leaf nodes and moving upward. Additionally, the use of a global moves counter simplifies the implementation. As we traverse the tree, the counter accumulates the total moves required without the need for multiple passes over the tree. This ensures the algorithm remains efficient and easy to implement. The binary tree is represented by nodes, each with 3 attributes: val for the number of coins at the node, and left and right for its child nodes. To track the total number of moves, we use a single global variable called moves. This approach avoids the need to manage complex return values across recursive calls. The algorithm's efficiency is clear from its complexity analysis. The time complexity is O(n), where n is the number of nodes in the tree, because we visit each node exactly once during the post-order traversal. The space complexity depends on the recursion stack. In the worst case, for a skewed tree, the recursion depth is O(n). For a balanced tree, the depth is O log n, making the algorithm both time and space efficient. There are a few edge cases to consider while implementing this algorithm. If the tree is empty, there are no nodes to process, so the function should simply return 0 moves. For a single node tree, no moves are required because the node already has 1 coin. Highly unbalanced trees, such as those where all nodes are on one side, are also efficiently handled by the recursive approach. This is because the algorithm processes each subtree independently, regardless of the tree's shape. The pseudocode begins by defining a class for tree nodes, and then a function called distributeCoins that initializes the moves counter and defines the recursive DFS helper function. The DFS function starts by checking if the current node is null, in which case it returns a balance of 0. The recursive DFS function continues by calculating the balance of the left and right subtrees using recursive calls. For each node, the absolute values of the left and right balances are added to the moves counter, representing the coins moved to or from the child subtrees. The function then computes the node's net balance by summing its coin value, the left balance, and the right balance, and subtracting 1. This balance is returned to the parent node to propagate any excess or deficit upward. Finally, the distributeCoins function calls DFS on the root node and returns the total moves counter, which contains the minimum number of moves required to balance the entire tree. This Python implementation solves the LeetCode problem number 979, distribute coins in binary tree. The goal is to ensure that every node in the binary tree ends up with exactly 1 coin, while minimizing the number of moves required. The solution revolves around a depth-first search (DFS) traversal of the tree. In this approach, we calculate the excess coins at each node, which represent the coins that need to be moved to or from that node. Here is a line-by-line explanation. 1. We define a tree node class to represent nodes in the binary tree. Each node has a value, val, a left child, and a right child. 2. In the solution class, the distributeCoins method is defined. This method initializes a moves variable to 0, which will track the total number of moves required. 3. The DFS, depth-first search, helper function is defined to recursively traverse the tree. The base case is when the node is none, in which case the function returns 0, no excess coins. For every node, we recursively calculate the excess coins in the left and right subtrees. This is done by calling DFS, node.left, and DFS, node.right, respectively. 5. The moves variable is updated by adding the absolute values of the excess coins from the left and right subtrees. These represent the moves required to balance the coins at the current node. 6. The function then computes the current node's total excess coins. This is given by the formula node.val plus left_excess plus right_excess 1. Here, node.val is the number of coins at the current node, and -1 accounts for the fact that the node needs exactly one coin to be balanced. 7. Finally, the DFS function is called on the root node of the tree, and the total number of moves is returned as the result. This solution is efficient because it processes each node exactly once, resulting in a time complexity of O(n), where n is the number of nodes in the tree. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Here, we start with the definition of the treenode class, which represents the nodes in our binary tree. Each node contains an integer value and references to its left and right child nodes. The constructor initializes the node's value and sets its child references to null. Then we have the solution class, where we define a private variable moves to keep track of the total number of moves required to balance the coins. The main method, distributeCoins, takes the root of the tree as input, initializes moves to 0, and calls the helper method DFS, which stands for depth first search. This method will recursively traverse the tree and calculate the necessary moves. If the current node is null, it returns 0, as there is no excess or deficit of coins at a non-existent node. This forms the base case for our recursion. Now, within the DFS method, we calculate the excess coins from the left and right child nodes by recursively calling DFS on node.left and node.right. The moves variable is then updated by adding the absolute values of left excess and right excess. This step accounts for the total number of moves required to transfer excess coins from child nodes to the current node or vice versa. Finally, the method returns the overall excess or deficit of coins at the current node, which is calculated as the node's value plus the excess coins from its left and right children, -1. The -1 is because each node needs to retain exactly one coin for itself. This return value is used to propagate the coin balance up the tree as the recursion unwinds. Here, we're working with a simple binary tree where the root node has 3 coins, and both of its child nodes have 0 coins. The objective is to distribute the coins so that each node contains exactly one coin. To solve this, we begin at the root node, which has a value of 3, and traverse recursively. First, we move to the left child. Since this left child has no children of its own, the excess from its left and right subtrees is both 0. Using the formula node_value plus left_excess plus right_excess 1, we calculate that this node requires one coin, returning an excess of -1. Returning to the root, we now know the left subtree contributes an excess of -1. Next, we traverse the right child, which has a similar structure and calculation. This node also has no children, resulting in a left_excess and right_excess of 0. It also requires one coin, returning an excess of -1. At the root, we combine the excesses from both subtrees, giving us a total of abs, -1, plus abs, -1, equals 2 moves. Finally, the root itself balances out with an updated excess of 0, indicating that no further redistribution is needed. The total number of moves required for this example is 2. In this second example, the tree is larger and slightly more complex. Here, the root starts with 0 coins, while the left child has 3 coins. The right child has its own subtree requiring further distribution. The goal remains the same, ensuring each node ends up with exactly one coin. Starting at the root, we first traverse the left child, which has a value of 3. This node has no children, so both left_excess and right_excess are 0. Using the formula, we calculate that this node has 2 excess coins, which it returns to its parent. Back at the root, we now know the left subtree contributes an excess of 2 coins. Next, we move to the right child, which has a value of 0. To handle this, we recursively traverse its left and right children. The left child of the right subtree has a value of 0, and since it has no children, both left_excess and right_excess are 0. This means it requires one coin, returning an excess of -1. Returning to the right subtree's root, we now traverse its right child, which has a value of 2. This node also has no children, so both left_excess and right_excess are 0. Using the formula, we calculate that this node has one excess coin, which it returns to its parent. Now, at the right subtree's root, we combine the excesses from its left and right children. The left child contributes -1, and the right child contributes 1, resulting in a total of 2 moves for this subtree. It then returns an excess of -1, meaning it still needs 1 coin. Finally, back at the overall root, we combine the excesses from the left and right subtrees. The left subtree contributes 2, and the right subtree contributes -1, resulting in a total of 3 moves. The root balances out with an excess of 0, and the entire tree is now balanced. The total number of moves required for this example is 5. In this last example, we have a perfectly balanced tree where every node already contains exactly 1 coin. Starting at the root, we traverse the left child. Since this node has no children, both left_excess and right_excess are 0. Using the formula, we calculate that this node is already balanced, returning an excess of 0. Back at the root, the left subtree contributes 0 excess coins. We then traverse the right child, which follows the same process. It too is already balanced with no excess coins to return. At the root, both the left and right subtrees have an excess of 0, resulting in no moves required for redistribution. The root itself balances out with an excess of 0, confirming that the entire tree is already balanced. The total number of moves required for this example is 0. The time complexity of our solution is O(n), where n represents the number of nodes in the binary tree. This is because we use a depth-first search, or DFS, to traverse the tree, visiting each node exactly once. Let's break this down further. First, the DFS traversal ensures that the DFS function is called recursively on both the left and right child of every node. Since every node is visited exactly 1 time across the traversal, the total number of recursive calls corresponds directly to the number of nodes in the tree, which gives us O(n). Additionally, for each individual node, we calculate the excess coins by evaluating node.val plus left_excess plus right_excess 1, and we update the total moves using the absolute excess values from the left and right subtrees. These computations are constant time operations, or O(1) per node. When you multiply the O(1) work per node by the total number of nodes, n, the overall time complexity becomes O(n). The space complexity of this solution is O(h), where h is the height of the binary tree. This arises from the memory needed to maintain the recursive call stack during the depth-first search. Let's go into more detail. At any point during the recursion, the stack will hold 1 function call for each level of the tree. In the worst-case scenario, the tree is skewed, meaning all nodes have only 1 child. In this case, the height of the tree equals the total number of nodes, n, and the space complexity becomes O(n). On the other hand, in the best-case scenario of a perfectly balanced binary tree, the height is logarithmic in terms of the number of nodes, or O log n. Beyond the stack space, no additional data structures are used, which means the remaining space usage is constant, or O(1). Therefore, the overall space complexity is determined by the height of the tree, O(h). To better understand the performance of our solution, let's analyze the best, average, and worst cases. In the best case, where the binary tree is balanced, the height of the tree is O log n. While the time complexity remains O(n), the space complexity is reduced to O log n due to the shorter recursion stack. In the worst case, for a completely skewed tree where every node only has a single child, the height becomes O(n), and both the time and space complexities are O(n). For an average case, where the structure of the tree is randomly determined, the height typically falls somewhere between O log n and O(n). Consequently, the space complexity will be within this range as well, while the time complexity consistently stays at O(n). When compared to brute force or naive approaches, which might involve multiple traversals of the tree to calculate and distribute coins iteratively, those methods could lead to a time complexity as high as O(n²) in the worst case. In contrast, the DFS-based approach achieves optimal performance by solving the problem in a single traversal, maintaining a time complexity of O(n). To solidify our understanding, let's mathematically prove the time and space complexity. For time complexity, let T, n, represent the time it takes to process a tree within nodes. Each node performs a fixed amount of work, O(1), and recursively processes its left and right subtrees. This can be expressed with the recurrence relation t, n, equals t, left underscore subtree, plus t, right underscore subtree, plus o, 1. Since every node is visited exactly once, the total work done is proportional to n, confirming that t, n, equals o, n. For space complexity, the maximum depth of the recursion stack corresponds to the height of the tree, which is h. This gives us O, h, space complexity. For a balanced tree, h is O, log, n, while for a skewed tree, h can be O, n. In summary, the time complexity of this solution is O, n, in all cases, and the space complexity is O, h, with h depending on the tree's height. This DFS approach is clearly optimal when compared to naive methods that involve repeated tree traversals and higher time complexity. When working on tree-based problems like this one, there are a few common pitfalls to watch out for. First, having an incorrect base case in your recursion can lead to major issues. For instance, if you fail to handle null nodes or leaf nodes explicitly, your recursive calls might keep going indefinitely, causing a stack overflow or incorrect results. Always ensure your base case is well defined. Another mistake is ignoring edge cases. Think about scenarios like a tree with only one node, a completely unbalanced tree, or a tree where all nodes have the same value. These situations might be rare, but they can easily break a poorly tested solution. Additionally, in depth-first search approaches, double counting is a frequent issue. If you don't carefully manage the state of your solution or understand what each recursive call is contributing, you might accidentally count the same nodes or paths multiple times. Finally, inefficient traversal is something to avoid. Some solutions might traverse the tree multiple times unnecessarily, which can significantly hurt performance, especially for problem constraints involving large trees. Always aim to minimize redundant computations to ensure your solution runs efficiently. Off-by-one errors are another frequent issue, particularly when dealing with trees represented as arrays. For example, calculating the indices for left and right child nodes in a binary heap can be tricky, and even a small mistake in your formula can derail your solution. Double-check your calculations to avoid these errors. Now, in an interview setting, pattern recognition is hugely important. Many tree problems follow predictable patterns like divide and conquer, depth-first search, or post-order traversal. Recognizing these patterns early can save you a lot of time. Also, be prepared to discuss trade-offs. For instance, recursive solutions are often elegant but can lead to stack overflow with large inputs, whereas iterative solutions avoid this but might be more complex to implement. Interviewers also like to test edge cases. By preemptively explaining how your solution handles these, you demonstrate thoroughness and an understanding of the problem space. Lastly, always optimize for the constraints given. If the problem specifies a constraint like n being at most 10,000, a solution with complexity worse than O, n log n, is unlikely to be acceptable. Aim for efficient algorithms that respect these limits. There are also several related problems that share similar concepts and can help deepen your understanding of tree algorithms. For example, LeetCode 543, diameter of binary tree, involves calculating the maximum distance between any two nodes, while LeetCode 124, binary tree maximum path sum, focuses on finding the path that yields the highest sum of node values. LeetCode 112, path sum, is another relevant problem, requiring you to determine if there's a root-to-leaf path with a given sum, and LeetCode 337, house robber 3, is a dynamic programming problem on trees. Exploring these can help you identify commonalities and refine your approach. Now, when it comes to tackling problems, there are a few approaches worth considering. A brute force method might be easy to implement but is usually inefficient, often having O, n squared, complexity due to redundant computations. Using depth-first search with memoization can significantly reduce redundancy by storing intermediate results, but it does require additional memory. Iterative traversal avoids the risk of recursion stack overflow but can involve more complex code, often requiring stacks or queues to manage state effectively. Finally, post-order traversal is particularly powerful in problems where child nodes must be processed before their parent. It's efficient, often leading to clean and optimal solutions for tree problems when used correctly. Great work! We've tackled the distribute coins in binary tree problem and explored a clean and efficient solution using recursion. Remember the importance of breaking down complex problems into manageable steps. Thanks for joining, and don't forget to subscribe for more problem-solving insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!